So here we have the final part of our trinity of exercises. So just a quick recap. In the first part of the exercise, we looked at the map A, the linear map, and then we showed that the origin there is a saddle point. In the second exercise, we looked at the map A mod 1, so that's a nonlinear map, and then we figured out that the point 1/3, 1/3 was actually a period 4 point of that map. And now the question is, combining these two pieces of information, can you also say something about the stability of that period 4 point? And the way we're going to do that is make a small perturbation from our fixed point and then see what happens when you apply the map one more time. Does it blow up? Does it converge towards 0? So pause the video, think very deeply about how you can combine these different pieces of information and then figure out what the stability of that period 4 point is. So let's indeed have a look at that perturbation. So we start not from our original point, which would be 1/3, 1/3, but we're slightly moving away from it. So by adding delta x and delta y. And then we apply that map one more time and we see what happens to that perturbation. Do we move closer to the point 1/3, 1/3, in which case it would be a stable fixed point? Do we run away from it, in which case we would have instability? So applying that map one more time. So the map in our case is a to the power 4, because we're looking at period 4 points. And then we should not forget to take the mod 1 operation, because this is our linear map here. Now, obviously, if we just focus only on the matrix multiplication here, that's a linear operation. So we can write that this is a4 1/3, 1/3 plus a4 delta x delta y mod 1. Okay, and we also know from the previous exercise that either we have the mod 1 operation at the very end, or we can also bring in extra mod 1 operations for the intermediate calculations. That doesn't really make any difference, because we're dealing here with linear operations, just summations and multiplications by a constant. So we can write this as a4 1/3, 1/3 mod 1 plus a to the power of 4 delta x delta y mod 1, and then we have another mod 1 operator at the very end. The good news is that we know what this thing is. We know that 1/3, 1/3 is a fixed point of that particular map. So this is indeed 1/3, 1/3. And then this part here will tell us how far away we move from our fixed point. Now, obviously these deltas, they're very small numbers, so we can make them small enough such that the mod 1 operation doesn't really play a role. If these are small enough, then we will end up with numbers that are all smaller than 1. So in this case, we can get rid of the mod 1 operator. And then what we're left with is basically this linear map here, where we have a small perturbation from the origin, and then we apply the map A, in this case 4 times. But we do know that the origin, of which this now is a small perturbation, is a saddle point of our original linear map. So this contribution is a saddle point, and in general this will not go towards 0. It will only go towards 0 if you're on the stable manifold of this particular saddle point of our linear map. So on the whole, if we combine everything here, then we can also conclude that for the fixed point of the map A applied 4 times, mod 1, that the point 1/3, 1/3 will also be a saddle point, because for most of the directions, the perturbation will run away. Only on the stable manifold here will it get to 0, the perturbation. So this is the final conclusion of this trinity of exercises.